Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to talk about limits as x approaches infinity. So I defined and talked about the limit in the previous video, and in this video I want to talk about a specific type of limit when x is approaching infinity. So if we were to take a look at the function 1 over x, which if I were to draw it, looks something like that. And if I was asked to find the limit of this as x approaches infinity, if you think about what that means, it's saying as x gets larger and larger and larger and larger without bound, what happens to 1 over x? And you can see on the graph that the function 1 over x is getting smaller and smaller and smaller, and in fact will approach 0. It will never equal 0, but the limit of 1 over x as x approaches infinity is equal to 0. If we had the next example, the limit of 2 over x as x approaches infinity, the graph would look very similar. The denominator is still getting large without bound. The numerator is staying constant, but the denominator is getting large without bound. So it too will approach 0 as x approaches infinity. So the limit of 2 over x as x approaches infinity is 0. You could have numbers added or subtracted in your denominator. It won't affect the fact that your denominator is getting larger and larger and larger without bound. So the limit of 1 over x minus 4 as x approaches infinity is 0 as well. If we have a higher power of x, it just gets larger faster. So it still approaches 0, it just does it a little bit faster. So the limit of 1 over x squared as x approaches infinity is 0. When you have a constant in the numerator, it doesn't affect it. If you have a coefficient in the denominator, it doesn't affect it. Our numerator stays a constant value of 5. Our denominator gets larger and larger and larger. So as x approaches infinity, 5 over 3x will approach 0. Let's take a look at what we do if we have x in both the numerator and the denominator. So in this next example, if I have x in the numerator and the denominator, both the numerator and the denominator are going to get large without bound. This does actually approach a specific value, and you could find that value if you set up a table of values and then just pick values of x getting larger and larger and larger and evaluate what this function would approach. That's very tedious and time consuming, so instead I'm going to show you a strategy that you can use. What you can do when you have x in both the numerator and the denominator and x approaches infinity is divide by the highest power of x in the expression. So in this case, my highest power of x is x to the 1. So I'm going to divide by x, which is the same as multiplying by 1 over x. I do the same thing to the numerator and denominator. And remember, when you multiply your numerator, you multiply every term. A common mistake I see students make is they forget to write limit when we're not evaluating it yet, we're just manipulating the function. When we evaluate it, then we leave out the limit notation. So 5x times 1 over x will be 5, minus 1 times 1 over x. In the denominator, 6x times 1 over x is 6, plus 2 times 1 over x is 2 over x. And by using that strategy, you end up with a fraction that contains terms that are either constants or fractions with x only in the denominator. And that's the goal, because then we can evaluate what the limit is as x approaches infinity. So now I can evaluate this. The limit of 5 as x approaches infinity is just 5, minus 1 over x approaches 0 as x approaches infinity. In the denominator, the value of 6 as x approaches infinity is still 6, plus 2 over x approaches 0 as x approaches infinity. So the limit of this as x approaches infinity is actually 5/6. And if you think about it, I think that it makes sense, because if you take a look at 5x minus 1, if we put 1,000,000 in for x, it's just going to be just about 5 million in the numerator. The denominator will be just over 6 million. Then if we put a larger number like 1 billion, we're going to have one short of 5 billion in the numerator. We're going to have two more than 6 billion in the denominator. Similarly with trillion, we can keep getting larger and larger, and these numbers get really insignificant when you're talking about those large values. So you're going to have 5 times this huge number divided by 6 times this huge number. So this fraction would approach 5/6 as x approaches infinity. In my next example, I have 2x plus 7 in the numerator. I have 3x squared minus 4x in the denominator. So I actually have a higher power of x in the denominator. So you might be thinking, well, that means that the denominator will get larger faster than the numerator as x approaches infinity. I'm going to, the strategy that we're going to actually use to find this is we're going to divide by the highest power of x in the whole expression, and our highest power is x squared. So I'm going to multiply the numerator and the denominator by 1 over x squared. Dividing by x squared is the same as multiplying by 1 over x squared. When I do that, I'll be left with terms that are either constants or fractions where x is only in the denominator. So 1 over x squared times 2x will be 2 over x. 7 times 1 over x squared will be 7 over x squared. In the denominator, 1 over x squared times 3x squared will be 3. And 4x times 1 over x squared will be 4 over x. So I don't have x's in any of my numerators, which was the goal. I can find the limit of this expression by finding the limit of each of these terms as x approaches infinity. So 2 over x will approach 0 as x approaches infinity. 7 over x squared will approach 0 as x approaches infinity. 3 stays 3, it doesn't matter what x is doing. And 4 over x will approach 0 as x approaches infinity. So the limit of this expression as x approaches infinity is 0. And that makes sense because we know that our denominator is growing without bound faster than our numerator. In this example, we have x in both the numerator and denominator. So we know that both the numerator and denominator are going to get larger without bound. But you may be thinking, well, my highest power is in the numerator, so the numerator is going to grow faster than the denominator. And what does that mean? So let's take a look. Let's use the same strategy. Let's divide the numerator and the denominator by the highest power of x, which in this case is x to the 4th. So dividing by x to the 4th will be multiplying by 1 over x to the 4th. Don't forget to write your limit notation, because I haven't evaluated anything yet. We're just manipulating this expression, and then I'll take a look at finding the limit. So 5x to the 4th minus 1 over x to the 4th will be 5, minus 2x times 1 over x to the 4th will be 2 over x cubed. 3x times 1 over x to the 4th will be 3 over x cubed, plus 1 times 1 over x to the 4th. Now I have an expression where every term is either a constant or a fraction where x is only in the denominator, which is perfect because now I can find the limit. The limit of 5 as x approaches infinity is still 5. The limit of 2 over x cubed as x approaches infinity is 0. Similarly, the limit of this fraction as x approaches infinity is 0, and same thing here. Hopefully you recognize we have a problem. We have division by 0, which is undefined. So So this is telling us that the limit does not exist. As I mentioned, our numerator is getting larger without bound faster than our denominator. So the numerator is getting larger and larger and larger. And as x gets larger, it's going to become more obvious. So this actually will approach infinity as x approaches infinity. I want to talk about one other type of example you may encounter with limits, and that's something like this, where you have the limit of the square root, in this case, of x minus 2, and x is approaching -1. If you were simply to plug -1 in there, you're going to get square root of -3, which is an imaginary number. It's not a real number. So the problem with this question, if I were to draw this function, it would look like this. And you can see that the function isn't defined anywhere near x equals -1. So how do we know what's happening to the function as x approaches -1? It can't approach -1 because it's not defined anywhere near that. So we would just say x cannot approach -1, therefore limit does not exist. So you'll probably encounter questions similar to that as well in your limit exercises. I'm going to move on now to differential calculus, and I'm going to start with talking about the slope of a curve and a derivative. And in order to do that, I have to use limits in my definition. So hopefully you have a fairly good understanding of what a limit is and how to find it, because that's what we're going to be using in the next few videos. All right, take care, and we'll see you then.